So now we talk about the three important aspects of whatever we learned till now. We'll just combine few concepts to build up the newer concepts. So let's see what are the very new concepts we'll learn in this particular session. Now let's go back to the slides. So here we'll learn the combined statement of first law and second law of thermodynamics. Then we'll go to the third law of thermodynamics, and then we'll introduce the concept of Gibbs free energy. Once you master this three concepts along with the calculation of entropy and enthalpy, you almost cover to 30% of problems that are asked. 30%, I'm telling you. 30% of your 30 to 35% of questions are normally being asked from entropy calculation, enthalpy calculation, Gibbs free energy, and all these questions are asked. And so it's so important. So once you learn this, you cover to 35% of the questions asked from thermodynamics in metallurgy, in gate metallurgy. So now let's see what all this means. Okay, we'll start with the combined statement. We'll start with the combined statement of first and second law. Okay, combined statement of first and second law. Let's see what it is. So your first law, as I have been keep telling you, del Q minus del W. This is your first law. Your second law was ds is del Q reversible by T. Okay, so this has been your first law. This has been your second law. The definition of entropy. It's actually, and this is basically energy balance. Heat and energy balance. Energy balance equation. First law is basically an energy balance equation, and second law gives you the concept of entropy. Now I've already told you del W is the work done, pressure multiplied by volume, or in differential form we write as PdV. Now if you substitute del Q here, so you have del Q is TdS. Okay, so if you substitute del W and del Q, you will get du equal to TdS minus PdV. Du is equal to TdS minus PdV. So this is the second law. It's a combination of first and second law of thermodynamics. This is called a combined statement of first and second law of thermodynamics. We'll see why we'll derive this equation, why this is important. We'll see when we'll go to the clauses, Clapeyron equation, Maxwell's equation, where we'll talk about different transformation of equation. Those are also asked. That analytical substitution. We'll see that in that particular chapter. But for now, this is du equal to TdS minus PdV. Let's now quickly review the third law of thermodynamics. Okay, third law of thermodynamics. Third law of thermo. We normally call it as thermo. Student guys also call it thermo. Anyway, so what does third law says? One for a perfect crystalline solid is the first parameter. Second is at absolute zero, that is 0 Kelvin. which is also an a conceptual thing. This doesn't occur. 0K is doesn't occur. The entropy, the absolute value of entropy of a perfect crystalline body at 0K is 0. Okay, so S, the entropy, is not the change, it's the absolute entropy. So you're talking about change in thermodynamic parameters, but here we are talking about absolute entropy. So what does this really mean is that at absolute 0K there is no randomness, everything is freezed. So absolutely low temperature to minus 298 degrees centigrade. So minus 298 degrees centigrade, 273 degrees centigrade, sorry, minus 273 degrees centigrade. Absolutely the freezing temperature. At this temperature the entropy, absolute entropy of a crystalline solid, a perfect crystalline solid, is 0. So this is the third law of thermodynamics. I just mentioned it. We'll see why I mentioned it. Now we'll go to calculation of Gibbs free energy. It will be the most important. Why this is important, we'll see. Gibbs free energy, denoted by G. Now, few things you should quickly remember. G is expressed as H minus Ts, and del G is del H minus T del S. It is probably the most important formula in thermodynamics. Normal for any calculation for class 2 for metallurgy. Most used and most important formula of all the formulas you will ever use in metallurgy. Del G is del H minus T delta S. So the change in free energy is expressed in terms of change in enthalpy and in change in entropy at a particular temperature. Okay. So there are a few properties of free energy. One, free energy determines whether process will move forward, process is feasible, it tells. Other thing is that it tells the equilibrium condition of any reaction, and at equilibrium del G equal to 0. This is very important. Del G equilibrium equal to 0. So for del G less than 0, forward process is favorable and spontaneous. 5, del G greater than 0, process is not spontaneous and is not favorable. Okay. So del G less than 0, process is favorable and spontaneous. So negative del G means, for example, just give you an example. We'll also solve some problems. So this slide is very important. You can pause it and note these important points. This is one of the most important points. Del G equilibrium equal to 0. So at equilibrium between liquid and solid, you can talk about phase transformation or any equilibrium. Where what is equilibrium? There is no change in mass transfer. There is no change in temperature. There is no change in pressure. That's what you call it, equilibrium. Okay. So just a bit more on free energy. So how will you calculate? R1 plus R2, let's say at a temperature T and pressure P, gives rise to R3 and R4. Okay, so R1 plus R2 reacts the temperature and pressure to gives rise to R3 and R4. So if you were asked the change in free energy, or whether R1 or R2 will at all convert at this temperature and pressure to R3 and R4, whether it will proceed in this direction, you will always calculate these things from free energy. So you need to find the free energy for minus R1 plus R2. That's what you need to calculate at this particular temperature, at this temperature and pressure, which is change in the enthalpies of the product side, R3 plus R4 minus R1 plus R2 minus T, change in the enthalpies of product side, okay. So change in the free energy at that temperature and pressure, temperature and pressure. So you do the subtraction and you will get the free energy change. So if this is less than 0, delta G is less than 0, it will spontaneously move in the forward direction. It's greater than 0, it won't move in the forward direction. You have to give higher temperature or you have to increase the pressure to do something else so that the delta G becomes negative and it moves in the forward direction. And if it is delta G is 0, that means R1 plus R2 is at equilibrium with R3 and R4. That is, there is no change in temperature and pressure will be there, and these systems will coexist. Equilibrium means coexistence. R1, R2, R3, R4 will coexist. So at this temperature and pressure, if delta G is 0, right? Okay.